Over the past videos, we have taken a look at each era in astronomy, starting with Aristarchus of Samos and working our way up through Newton to see how we got to what we know today about the orbits of the planets compared to what we see in the sky. What I'm going to do now is basically a lightning round overview of all the things that we went through in that time, from what the ancients saw and what we still see today, and how they got through to modern astronomy, to our modern understanding of how the planets move and how that results in what we see in the sky. So what the ancients saw is that the sky moves from west to east in a 24-hour cycle. But there are anomalies in there. For example, over the year, if you go out at roughly the same time of night, you see different stars. And so over the time of a year, we see that each night the stars creep west compared to the sun a certain amount each day. And so basically what they saw was the sky is moving, the stars are going at one rate, the sun is moving a little slower, so it falls behind, and so over the year we see the stars at the same time of the night would move a little bit west each night. Plus, embedded among those stars are a number of wanderers, or planetae, or planets as we call them now, that also move a little bit slower, but not quite as slow as the sun. So as we see them go through different parts of the sky, the sun will catch up with them and overtake them. And then another anomaly is that there are two of these planets that never strayed far from the sun. So let's take a look at what Aristarchus of Samos had to work with, where he came up with his idea that the sun was the center of the universe as we know it rather than the earth. So let's take a look at the western horizon. At some evening, the sun has set, so the sun is somewhere below the horizon. And we have, among our other stars, which we'll ignore for right now, we will see, just because we're lucky at this particular time, we see two of these stars. In fact, right now as I make this, we just passed a point where we could see both Venus and Mercury in the evening sky. But what did they do? Mercury and Venus never stray far from the sun. So we go and look at them one night, we see them like this. The next night at the same time, so the sun is the same distance below the horizon, it's just starting to get dark, and we see that, well, let's just look at one at a time so we don't get too confusing. So let's go to a particular time and we see, aha, I see Venus for the first time out there above the twilight. The next night, it's a hair higher at the same time. The next night, it's a hair higher. And I'm showing this at an angle because in my mind, I don't forget that the sun, the moon, and the planets roughly follow a path in the sky that's centered on the path of the sun, which we call the ecliptic. And so we see Venus gets a little higher and a little higher. Each day it's a little higher. Now, of course, everything is still going around every 24 hours, but we're looking at the same time each day compared to the sun, and we see Venus gets higher and higher. So like I said, the sun is going slower than the stars, but the planets are going slower than the sun. So the sun is falling behind, so the stars are going a little further each day. So as we're watching the stars, let's say I'll pick two stars that are fairly close to the ecliptic. We have Castor and Pollux, the brightest stars in the constellation Gemini, which in the late spring, early summer are roughly aligned like that along the horizon. While Venus is going up, each night these are a little lower. So the sun is going to the east, causing these stars to be a little lower each day, but we see Venus is actually getting a little higher because it's going even slower than the sun. But after a while, if I wanted to be accurate, this kind of go all over the sky because the ecliptic is moving as we go through the year, but let's just keep it simple. We find it gets to a peak height, and all this time it's getting brighter and brighter too. But if we finally get to a peak, and then it starts going back down and gets brighter and brighter and brighter, and eventually gets extremely bright, becoming the third brightest object in the sky after the sun and the moon, and then rapidly dims and disappears back into the solar glare. So now, a couple of weeks later, we run out, and Now, instead of looking west, we're going to turn around, and now we're looking east, and the sun is about to come up. So here comes the sun. We see the whole sky rotating at an angle because we are not all standing on the equator. If you are on the equator, you see everything go straight up, but most of us are north of the equator, so we see it at an angle. But we see, a couple of weeks later, we see Venus appear out of the twilight, and then it climbs higher and higher, rapidly getting brighter, getting very, very, very bright, once again becoming the third brightest object in the sky. Then it gets higher and higher and higher, dimmer and dimmer and dimmer, turns around and goes back. So what did Aristarchus conclude when he saw that? He sees in the morning, Venus comes up day by day by day, day by day by day, goes back down. Then in the evening sky, at the same time, looking at the west, we see Venus come up and go back down. Looks to me like Venus might be going around the sun, right? So whatever else is going on, Venus is going around the sun. And don't forget Mercury. Mercury is doing the same thing. So in the evening sky, we'll see Mercury come up, do exactly the same thing, not as high, not as bright, and a lot faster. Mercury comes up, comes down, gone. And then in the morning sky, Mercury comes up, goes back down, and it's gone. It does that 3 times a year, where it takes a year and a half for Venus to go through this whole cycle. Evening sky, morning sky, evening sky, morning sky. Takes Mercury a third of a year, so like 4 months to do exactly the same thing. But nevertheless, neither Mercury nor Venus ever gets far from the sun. So Aristarchus established that Venus and Mercury go around the sun in some kind of a shape. But all we see from here is they go up and down. But what Aristarchus said, well, we must have the sun out here. There's the sun somewhere. And the earth is over here. And somewhere in between, we have Mercury going around the sun and Venus going around the sun. And if we are looking at the sun, if we see the sun in that direction, what are we looking at? Well, we're looking down on top of the solar system, so we're kind of on the edge of the earth. On the side of the earth, you look on a globe, where are we? On the way the globe sits on your table, where are we? We're on the side. We're not standing on top of the globe. And we're looking out there, so we're looking in this direction is the evening sky, and we're looking in this direction is the morning sky. And so when the sun gets below the horizon, we get this geometry we're looking at here. But he concluded that Mercury and Venus must orbit the sun. Now, what does the sun do? Well, Aristarchus, as we learned earlier, had calculated the size and distance of the sun and the moon relative to the size of the earth. What did Aristarchus figure out about the earth and its role here? Is the earth at the center, or is the sun at the center? Well, recall that Aristarchus had calculated the size of the moon relative to the size of the earth and the relative distance. He had no way of calculating the exact distances. He had no tools to do that, but he could calculate the relative distances like we explained in the video about Aristarchus. So he figured out about how far the moon away was from the earth, and he figured out that the moon was about 1/3 the size of the earth. It's actually closer to 1/4 the size, but he was pretty close. And he was very close on his distance, relative distance to the moon. But the sun in the sky is the same size as the moon on average. Sometimes it's a little bigger, sometimes it's a little smaller. So the sun is further away than the moon. And he also calculated, as we explained in his video, the relative distance to the sun, and he calculated it was 27 times as far away as the moon. So he calculated that the sun was tremendous in size compared to the earth and the moon, not as big as it really was, but much bigger, and he thought it's illogical for the huge sun to circle the earth. Now, when we see the sky rotate around the earth, what's it look like? It looks like the sky is rotating around the earth. But even average ancient people were not dumb. So the ancient philosophers wondered, is it the entire universe that rotates around the earth? Or is it the entire universe that's stationary with the earth rotating? And how can you tell which? You can't. I don't remember who it was, but there's a famous quote among physicists and astronomers about a student who noted to a teacher that ancient people must have been pretty stupid to think that the sun went around the earth. And the teacher said, yeah, they must have been pretty stupid. But I wonder what it would look like if the sun did go around the earth. In other words, he's saying you can't tell the difference. So Aristarchus was one who decided it doesn't make sense for a huge sun to go around a small Earth, it makes much more sense that the Earth is rotating, and now that puts everything stationary with the Earth rotating. So the sky is not really rotating around the Earth as it appears, but it's the Earth that is rotating with everything else stationary. And so now we have the Aristarchus model of the solar system, which is the sun at the middle. We already determined that Mercury and Venus are circling the sun, but the other planets don't. So where is the Earth? Well, he correctly stated that the Earth is the third one. So Mercury, Venus, Earth. And he also correctly figured out that Mars was next. How far? He didn't postulate on the distances or the size and shapes of the orbits, just the fact that of what order they were. So he had Sun, Mercury, Venus, Earth, Mars, and then twice as far away as Mars we know now is Jupiter. So Mercury, Venus, Earth, Mars, Jupiter, and then about another same distance from Mars to Jupiter. Do that same distance again. We've got Saturn out there, and that's all they could see in those days. There was no Neptune and Uranus or Pluto because although Uranus is visible to the naked eye under really good conditions, nobody had ever spotted it. So Mercury, Venus, Earth, Mars, Jupiter, Saturn. That's what Aristarchus came up with. And so we now have the Earth here spinning round and round while everything goes around the sun. So that's what Aristarchus came up with. Then we move on to Ptolemy, who rejected the idea that the Earth was rotating because logical reasons. He said that there would be tremendous winds as the Earth rotated inside the air, which everyone assumed just kept on going out. It was actually Copernicus who said, well, this atmosphere around the Earth is being dragged around with it, so whatever's close to the Earth rotates with it, but what's far away does not. It took a while for us to figure out that there's actually a vacuum out there and that the atmosphere around the Earth is actually a very thin layer that's being held on by gravity and dragged along with it as it spins. So Ptolemy rejected the idea of a spinning Earth, and Ptolemy also said, well, if I dropped something, if the Earth was spinning, it would go off to the side. There was a concept similar to momentum in those days, and so not everybody believed that, but that was something that some philosophers said the Earth can't be rotating because of that. But anyway, so Ptolemy comes along, and he puts the Earth back at the center. And he puts the sun out there orbiting the Earth. And Mercury and Venus are also orbiting, but somehow they're locked into the sun so that they go a little faster, a little slower, a little faster, a little slower. So we'll get to how he dealt with that later. And then we have Mars, Jupiter, and Saturn. But he made these all perfect circles because why not? I mean, they're up in the heavens. They must be perfect. So he had these circular, but he did have some problems to deal with. And to look at those problems, let's just simplify things a little bit. And we're going to go put the Earth at the middle of the universe and the sun orbiting the Earth. Now, is the sun orbiting the Earth or is the Earth orbiting the sun? You can't tell. And what we're going to figure out here, if it turns out to be the sun, it's the sun doing this motion that I'm explaining. But if the sun is in the middle, it's simply the Earth doing the motion. You just can't tell which is which. So we're going to use the sun because we can observe that. And so just to make it simple, let's simplify the year. You may have noticed that the year is 365 days, and we divide a circle into 360 degrees. And that's not a coincidence, because ancient astronomers used to divide the year into 360 days plus 5 extra days. And there's a word for that, and if I could remember it, I can't pronounce it anyway, so there it is. So there's 5 of these extra days to make up the whole year, or they made other ways to make the whole year even out. So let's say we do have a 360-day year, just to simplify things. So now here's the Earth, there's the sun going around the Earth in a nice perfect circle every 360 days. And so what's the sun going to do? Every day it's going to move 1 degree across the sky. How did they measure the sun against the stars if they couldn't see them? They used geometry to figure out where the sun was among the stars, even if they could not see the stars behind the sun. So every day, 1 degree, perfectly over the whole year. But by Ptolemy's time, they had accurate enough measurements. They weren't perfect yet by any means, but they were accurate enough to see that this did not work. Sometimes it went less than a degree. That would be like in the summer in the northern hemisphere. When I talk about summer and winter, I'll be talking about the northern hemisphere. So those of you in the southern hemisphere, you flip that around. So in the summer, the sun was moving less than a degree per day. But in the winter, it was moving more than a degree per day. So how do we deal with this? Well, Ptolemy had a way of dealing with it. He put the circle that the sun circled on, I won't be able to draw this perfectly, but he put the earth off center. That partially compensated for it. But he also put the sun on a second circle so that the sun went in the big circle and the second circle. Now, just simply putting the circle offset partially compensated, but not perfectly. So he had to make another circle, which we call an epicycle, with the sun going around there. So the sun's going around this way and the sun's going around that way. So the sun is basically doing these curlicues around this off-center circle. That almost compensates for all of what they were able to measure. But to make it perfect, he also had to put a point at the center of the circle and another point opposite the Earth by the same distance that he called the equant. And he did his math so that if you observed from here, so we are here on the Earth, but his math assumes we are observing from this point called the equant. And now he's able to get a very close approximation of the actual movement of the sun across the sky. And I got these curlicues are probably too close together, probably more closer to one big curlicue over the year. So if I want to be more accurate, that's what we think of when we think about epicycles, but it's probably more like, okay, here's the sun on its circle, and it takes a year to go around its circle, same direction, and so over the year it kind of does something like that. So the eventual path of the sun is an offset, not sure exactly what shape that would be, and the mathematics worked that if you looked from the equant, it would be a very close approximation to the actual motion of the sun across the sky. Now, we know that the sun is not the one that's moving, so you just flip them around, make this the sun and that the earth. Everything else is the same, and the math works the same, and we still have now the earth out there, but of course Ptolemy never used that. So that's the way Ptolemy made up for the non-uniform motion of the sun through the sky. And we had the same thing with, let's put the Earth here. We had the same thing with Mercury and Venus and Mars. And so every one of these was on, we have the Earth here. The circle is offset from the Earth, and the observation point or the equant was on the opposite side of the center. So here's the Earth, there's the center of the circle, there's the equant, and there's the epicycle. Every single orbit. Earth, center, equant, epicycle. Earth, center. So it was a kind of a complex system, but the mathematics worked that you could predict where a planet would be on a particular day, or you could go backwards and see where a planet was on a particular day. And so that's how Ptolemy solved all this. Then along comes Copernicus, who goes back to the idea of a heliocentric system. And it's arguable as to whether Copernicus was going back to Aristarchus to say, hey, I think Aristarchus was right. Some historians say that he did not. But Copernicus did talk about Aristarchus in his writings. So he was aware of Aristarchus and what Aristarchus did. So he very well could have based his ideas on what Aristarchus originally came up with. So he puts the sun back at the middle with the Mercury, Venus, Earth, Mars, Jupiter, and Saturn. And to make his math work, he did things a little differently. So let's just take a look at the Earth and the sun real quickly. So here's the sun, here's the Earth orbit. And he still had off-center circles and epicycles, but he used them differently. So we have the sun, it's already off-center. So there's the center of the circle, there's the sun, and this circle is going around, and the Earth is on a epicycle, but instead of the epicycle going the same direction, it went the opposite direction, such that the result was that as the Earth goes around the sun this way, it's rotating the opposite direction, and if we start out with the Earth here, by the time it gets over here, the Earth is there. By the time it gets here, the Earth is there. By the time it gets here, the Earth is there. So there's the center of the epicycle. But the Earth is always the same orientation in space. The result being that the Earth orbit, if I can draw this right, is offset. A terrible drawing there. Let me redraw this so we get the idea. Here's the sun. Here's the center of the circle. There's the circle. And the actual orbit was going to be something offset. So we have a perfect circle here. And what Copernicus was able to do, which won him over to most of the astronomers of the day, is he got rid of the equant, because they didn't like that observing from a place that nobody could observe from. So Copernicus worked out a math with the sun at the middle, where the planets had perfectly circular orbits. And the reason Copernicus wanted perfectly circular orbits was not philosophical or religious, but because to have anything non-circular would take some kind of force speeding them up and slowing them down. And so he was able to work out the math where he got a good close approximation of where the planets would be using a circular orbit, circular epicycles, in such a way that he got an orbit that matched observations close enough without that equant. So that's why Copernicus won people over with his heliocentric system. And the historians tell us that for 1,500 years, everyone believed Ptolemy and nobody had any idea of a heliocentric system. That's not true. There were arguments going on, but people accepted the Ptolemy system because he'd worked out the math and nobody had gone through the trouble of working out the math for a heliocentric system. And the only reason Copernicus did is because he was an amateur astronomer. He did this in his spare time. His full-time job was a cleric for the church, not a ordained priest, but somebody who did clerical work for the Catholic Church. So in his spare time, he worked this out, and he didn't even publish it until late in his life because he didn't want to cause any trouble. So now we're to the point where we have the sun at the center, Mercury, Venus, Earth, Mars, Jupiter, and Saturn, and we have a math that works it out that way, so we don't have to go back to Ptolemy and use the geocentric system to work out the positions, whether or not we understand that it's really heliocentric. We have a heliocentric system where the math works. Thank you, Copernicus. So now along comes Tycho Brahe, and his claim to fame was that he made huge measuring instruments, put them on solid ground below ground level so they'd be out of the wind, and made the most accurate measurements of the positions of the celestial objects before the invention of the modern telescope. So now we have these very accurate positions, and Copernicus's math doesn't quite work. Along comes Johannes Kepler, and he wants to figure out what is the actual shape of these orbits. What can I figure out to get the actual movements, not necessarily having a circular shape in all these epicycles? How can I simplify this? And Kepler first rejected the idea of elliptical orbits because he said if it was that simple, somebody else would have thought of it. Well, it was that simple and nobody else had thought of it. So let me talk about what an ellipse is. If we take a circle, in the middle we have the center of the circle. But an ellipse is somewhat egg-shaped, but it's the same on both ends. This is not a perfect ellipse by any means. Here's what a perfect ellipse looks like. But an ellipse, instead of a center, has two foci, which is a plural for focus. So I have one focus here, one focus there, two foci. And if you want to draw an ellipse, if you take a piece of string and run it through a couple of pins on a board with a little bit extra room, so we make a triangle. So you put a stick pin here, a stick pin here, put a writing pin up there, and you drag that around, making sure that this stays tight on the stick pins, and you will draw an ellipse. Another thing about an ellipse is, if we have the two focuses, let's say we have an elliptical shaped basin of water, and we drop a drop of water here and we get a wave that goes out. It's going to reflect off the sides, go across, and then it's going to hit these sides and reflect off and all combine right there, and then it goes back out and does it again back and forth. It's a couple of things about an ellipse, but an ellipse is this particular shape. And Kepler did not look at an ellipse at first because he thought if the planet's orbits were elliptical, someone else would have figured that out. So he tried trial and error, put the sun at the center and had, let's just take a look at Mars because that's the one he figured out first. We have Mars going around the sun. What shape of this orbit that he could do calculations to figure out where the planet would be at a particular time that matched the observations. And here's the trick. You may have already thought of this. He's trying to measure this from the Earth. So here's the Earth moving. Here's Mars moving. How do I figure out where Mars is when my observation point is moving? Now, if I could stand at the center of the sun, that would be perfect. I could get perfect measurements. But I can't. I'm on the moving Earth. But Tycho Brahe had made these very accurate measurements. And of course, he made measurements when Mars was at opposition. So let's take a quick look at what he did. Let's put the sun here. Here's the Earth's orbit. Here's Mars's orbit. And every roughly 2 years, a little more than 2 years, the Earth, the sun, and Mars line up. That's when Mars is at opposition. So the sun's in one part of the sky, Mars is in the other part of the sky. So when the sun is setting, Mars is rising. We're not going to see it, the sky's too bright. But as the time goes by, we see Mars straight up overhead, the sun is directly below. Sun, Earth, and Mars lined up. And at those moments, when Mars was at opposition, observing Mars from the Earth was exactly the same as observing Mars from the sun. And so a little over 2 years later, he does the same observation. A little over 2 years later, he does the same observation again. He's getting all these observations with the Earth seeing Mars at the same place it would be if he was observing from the sun. So he does that over an entire Martian orbit, and now he has position for Mars along these points in the orbit. He just had to now figure out what shape and what math he could use to get the distance between here and here and here to work out so that he could predict where Mars would be on this orbit. And so he tried different shapes, and finally he tried the ellipse, even though he thought couldn't be an ellipse. Someone would have figured that out. And that's the one that fit. And what Kepler figured out, and we're not to the point where we understand gravity yet. We know gravity exists. You know, Newton did not discover gravity. Everyone knew about universal gravity, and that the idea that when something falls, it falls toward the center of the Earth, that was already known. It's just that Newton, who had time on his hands during a pandemic, figured out what's going on in space with gravity. But back to Kepler, we have the sun at the center, and I'm going to exaggerate this quite a bit. This is a very eccentric ellipse. Terrible drawing though. What he found is that if you have, let's say that took 1 month for the planet to sweep across this part of the ellipse here, when it got out here where it's moving slower, when the planet was closer to the sun, it was moving faster. We already kind of saw that. Remember, they've discovered that over the year, the sun appeared to move more than a degree per day during the winter and less than a degree per day during the summer. Well, guess what? The Earth is closer to the sun in the winter than in the summer. So when the planet is close to the sun, it's moving faster, and when it's away from the sun, it's moving slower. So what Kepler finally figured out was that the area of this triangle here is identical to the area of this triangle there. So equal area over equal time. 1 month to go that distance, 1 month to go that distance, or a month to go this distance. And notice that it sweeps less distance, but the triangle is longer, so it has the same area. So that was Kepler's law, that the object in orbit sweeps out an equal area. If you do the geometry, the area that it sweeps out is equal for equal time. And that's how he figured out the elliptical orbits. Now, of course, we look at the orbits. They're usually drawn as circles, right? Because they're pretty close to circles. Here is a diagram of the inner planets. This would be Mars through Mercury. You can find this at heavensabove.com if you look at the solar system chart. And it shows where the planets are relative to each other, where the summer solstice is straight down, so the vernal equinox is to the left, the autumnal equinox is to the right, and the winter solstice is up at the top. So this shows the relative positions of the planets, but notice the circles. They're not all concentric, and if you look carefully, they're not all perfect circles. Venus is the closest to a perfect circle, but look how different from a circle and how much offset Mercury and Mars are. They're quite eccentric. They look like circles, but they are actually nearly round ellipses. In fact, a circle is an ellipse where both foci are at the dead center. You start to move those foci apart, you start to get an ellipse. And so Venus, they're very close together, so it has a nearly circular orbit. Earth, they're a little further apart, so there's the center, there's the other focus. A little further apart with the Earth, so the Earth has a slightly more eccentric orbit. But all of the planets have fairly circular orbits. But you get a comet coming in, they tend to have very elliptical orbits. So you have a comet come in, so there's like Halley's Comet, goes up near Neptune, and it's a very eccentric elliptical orbit. And a lot of comets have such eccentric orbits that nears makes no difference. These are parallel, so because they come from so far away. And once in a while we have an object come through the solar system where it's so far away that the orbit is hyperbolic, where those lines never get parallel. But at any rate, that's what Kepler figured out, is that the orbits are elliptical and the planet sweeps out an equal distance for an equal time. So finally we come to Newton, who has time on his hands. During a pandemic, he sees an apple fall from a tree, which is true. He saw an apple fall. It wasn't, people say that all the time. People understood gravity, but that made him think, I'm going to figure out the mathematics of this based on what Kepler found. And so Newton, not really too much to say about this. The accomplishment was great. Took a lot of work to find something fairly simple where he was able to calculate these orbits based on the amount of gravitational attraction between the two objects, how fast the object was moving compared to the assumed stationary central object, and where it was. So it's out here, it's further away. So if you double the distance, you cut the gravitational force by 4. That's called the inverse square law. So if I have two objects this far apart and there's X amount of gravitational force between them, if I double that distance, we end up getting X divided by 4. We double that again, then we get X divided by 4, if you will. So each time we double that distance, we cut the gravitational attraction by a factor of 4. And so we lose a lot of that out here, so we don't have a lot of gravitational attraction, but it's not traveling that fast. And as we get closer, we have more gravitational attraction. So I need to explain what Newton figured out. We're almost there. So as Newton explained in orbit, it works like this. I'm going to draw a picture of the Earth. And I'm going to put a little mountain. I'm going to put a cannon on that mountain. I want that cannon firing horizontal. So there's our cannon. Looks like a big blunderbuss up on a mountain. Now I'm going to fire that cannon. Cannonball is going to come out. Now this is the way Newton explained in orbit. The cannonball is going to come out. It's going to be going in this direction, but the Earth is pulling it in that direction. And so that's going to cause the cannonball to curve, and it's eventually going to hit the Earth. So I'm going to put more powder in there. I'm going to shoot the cannon harder, so it's going to go further. I'm going to put more powder in there and shoot the cannon harder. Now, we have to assume that this mountain is far enough that we're outside the Earth's atmosphere. So Newton had to assume that the atmospheric drag that we have here did not exist out in space. So there's our idea that we have an atmosphere where there's a vacuum in space. So this cannon is outside of the Earth's atmosphere, so that cannonball does not encounter any air resistance. We're going to put more powder in there and shoot it again, and it's going to end up there. Let's do it another time. Fire, it goes out and it makes it all the way to there. Nevertheless, it never makes it all the way around. But let's put enough powder in there, we shoot it, and around it goes, and eventually comes back to the same place, because what's happening? The cannonball is falling, but it's falling around the Earth. So it should have hit the Earth by the time it got here, but the momentum had carried it around to where it misses the Earth. It still has that momentum. It's still going in this direction. The Earth is still pulling it in this direction, so it ends up going to here and keeps missing as it's being pulled toward the Earth. Momentum carries it that way, and so it goes, and once again, you see the slight curve here. It's pulled toward the Earth, but momentum carries it around and just keeps going round and round. And that would be a perfectly circular orbit. We just now put just enough powder to get a perfectly circular orbit. Good luck with that, because it's very finely balanced. Let's put some more powder in. It's going to go a little higher. But then what's happened here? It's gone higher, and it's getting slower and slower because that Earth is still pulling on it. That's slowing it down. So it has the energy to go higher, but the Earth is pulling it toward it, so it's actually slowing it down. It's kind of hard to draw the geometry here, but I'll draw this extremely elliptical in a minute to make sense about how this works. But anyway, it slows it down, so now it doesn't have enough momentum to stay there, so as it goes around, it gets closer and closer and closer, and eventually hits the same place, but look what it did. It went up higher and then lower. So what I'm going to do is show a more elliptical orbit, and we'll see maybe a better visualization of how that happens. So here's our object right here, going at this speed. It's being pulled in that direction too, so it goes around. Now as it follows, now look here, we have a very highly eccentric orbit. The Earth is pulling in this direction, so it's slowing the object down. So it goes slower and slower and slower, and eventually gets way out here. And so it no longer has the momentum to stay out there, and we've got the gravity pulling it in. So it goes a little bit, but the gravity pulls it this way, so it starts to fall back toward. Gravity is getting stronger. It's getting more momentum though, so it's coming closer to the Earth, being pulled toward it, getting faster and faster and faster, and now finally passes here, but it's going too fast to stay this low, so it goes back around again. And so now we get that elliptical orbit. And so Newton figured out the mathematics. Now here's Newton's first law that explains the gravitational attraction, which basically says that the gravitational attraction is equal to the product of the mass of the two objects divided by the square of the distance between them, multiplied by the gravitational constant. So we have to throw in that gravitational constant to make this work, but that's how Newton figured out how the gravitational attraction works, and he also worked out the math to show how, okay, as we get further away, the Earth is pulling it back, it gets slower and slower. Out here no longer has enough momentum to stay out there, so it starts to fall back in, goes faster and faster. It has enough speed to stay in orbit, but too much to stay this close, so it slings back out again and just keeps going around. Fast, slow, fast, slow, fast, slow. And that's the nature of a highly elliptical orbit. We have the same exact thing with our nearly circular orbits we have now. Here's the sun, there's the Earth. If I can draw a nearly circular orbit, it is elliptical, but only slightly, but it's still elliptical. We still have, looks like we're closest here, fastest here, moving fastest, goes out, slows down, moving slower, comes back in, moving faster. So this is the North Hemisphere winter, and here's the North Hemisphere summer, and that's the nature of the orbits around the planets. So that's, in a nutshell, how we got to understanding how the orbits work. Each one has its own characteristics, but basically we have all of the planets. I was just showing that going counterclockwise, but if we're looking from the usual perspective, from the north-ish perspective, we have the sun here, and we see the planets orbiting counterclockwise. Mercury, Venus, Earth, Mars, and then Jupiter about twice as far as Mars, Saturn about twice as far as Jupiter, and there are the planets out there, all in their somewhat circular, but actually elliptical orbits. So the last thing I want to say is how this relates to what we see in the sky. So now let's take a look at what we can see in the sky. There's the sun, and there's Mercury taking about a third of a year to do an orbit. Venus taking about 2/3 of a year, and then the Earth taking a full year. So as we move along, let's start over here at the vernal equinox. So I'm doing just like that chart on heavensabove.com where the summer solstice is straight down, vernal equinox or spring equinox is to the left, autumnal equinox to the right, and winter solstice vertical. And let's just say at this time, double conjunction. We have Venus and Mercury right there. So let's say in 3 months Earth has gotten over to here, but Venus has gone way around in 3 months. Venus has gotten over to about here. Mercury in 3 months has done a complete orbit. So now Earth here, Venus there, Mercury's gone a complete orbit, it's back over there. And so when we're back over here with the Earth, Venus, Mercury, and the Sun lined up, we don't see Venus or Mercury unless they happen to pass in front of the Sun, which is, Mercury happens every few years. Venus does that every 100 years or so, so it doesn't happen every time they pass by because they are not perfectly lined, so they don't always line up perfectly with the Sun, so that we don't always see a transit as they move across the Sun. But unless they're in transit, we don't see them. But 3 months later, we see that Venus has moved to about here. Mercury's done a complete circle. And so now we're looking at the Sun. And look at this direction here now. If it's midday, we're standing on the Earth looking up at the Sun. But as the Earth rotates counterclockwise and we move over to here, let me just enlarge that. So midday, we're standing there. Mr. Stickman standing there looking straight up at the Sun. But the Earth is moving counterclockwise, so 6 hours later, we are standing over here. If I can draw another Stickman. So now we're looking roughly that direction at the Sun, and our horizon is on that line basically there as we watch the sun set. So what's happened? We're watching the sun set, so the evening sky is over here, and so we wait around another 12 hours, we end up over here. Now we're looking at the morning sky over in this direction. So there we see Venus in the morning sky, and Mercury we see in the evening sky. And Mercury's pretty well elongated from the Sun, so if the geometry is right, Mercury will be fairly high and we can see it if it gets elongated at this time of the year when the Sun is at the solstice. So let's take another 3 months. Things are going to change here. And let me erase that line because that's going to move. Let's go ahead and get rid of the Earth. Another 3 months, the Earth is going to move over here. And in that time, Venus is going to move to maybe about here. Mercury has done another complete orbit. And so now Mercury's on the opposite side of the Sun. If we are standing, let's put our little thing here. If we're standing here, looking straight at the Sun, that's the noonday sun. The horizons are that way. But 3 hours or 6 hours later, our stick figure's there. And so our horizon is moved there. And so there's the sun setting 6 hours later. And so now this is the evening sky, and that's the morning sky. So there we are there in the evening watching the sun set. 12 hours later, we're over here. Now we're watching the sun rise, and so there's the morning sky. And we see that Venus has gotten higher in the morning sky. It's no longer here. And it's actually about as elongated as it's going to get. Mercury's still sitting there. So Mercury seems to be in the same place each time because every 3 months it does a complete orbit of the, it's actually every 4 months, so I'm not quite perfect there. So it probably would have been here, and then now it's probably over here, but hopefully you get the picture there. So what we're going to see, if we go out the same time every day, once again, let's look at the horizon here. We're going to put the sun that far behind the horizon. We're going to see over time, we're going to see Venus eventually pop into the evening sky. As Venus catches up to us, it's going to get higher and higher in the sky. There's the horizon for the set sun. Venus is going to get higher and higher above the horizon. But when it gets here, what's going to happen? It's going to catch up and it's going to go between us. So it goes up and then back down. Mercury does the same thing. It just takes less time. It goes up and back down. It doesn't go as far. So in the evening sky, we just see Venus and Mercury go up and down. In the morning sky, we see them do the same thing. It's just that now they're over here. Venus gets higher and higher and higher, then lower and lower and lower. Mercury does the same thing. What do the outer planets do? Well, they don't go between us and the sun. So what we see the outer planets do, let's go look at our horizon again. This time we're going to look at the eastern horizon, looking east in the morning, and there's Mars. Way on the other side of the sun. So let me draw the diagram here. Here's the Earth. Here's Mars. So the Earth, let's put the Earth here, and Mars is here. I'm going to freeze the Earth here. As we go around, Mars is going slower, so Mars is going to fall behind. So this is the morning sky over here, evening sky over there. There's the Earth. We're on this side of the Earth in the morning, so there's the horizon line going to the sun. So we see Mars in the morning sky. So we see Mars fall behind, so it's get higher and higher. Mars gets higher and higher and higher. But Mars being an outer planet, or superior planet, Mars gets higher and higher and higher, and eventually Mars is going to come around and it's going to be at opposition. As the sun is setting, Mars is rising. In the middle of the night, Mars is straight up. In the morning, Mars is setting. And so it catches up, catches up, catches up, catches up. So once it gets here, let me clean up the geometry here. Once the geometry gets to where there's Earth and there's Mars. So here's the Earth, and as we see Mars come along, it's in the morning sky, rising earlier and earlier and earlier, and finally when it gets here, Mars is lined up. If it's the middle of the night, where's the sun? Straight down. So where's Mars? Straight up. And as Mars continues to go that way, as it falls behind the Earth, and Mars is falling behind, we're eventually going to see it get closer and closer to the sun and then disappear. We are moving this direction. Mars is moving a little slower, so as we go this way, Mars appears to fall behind and get higher and higher in the sky, and then works its way all the way around the sky until it's to the opposite side of the sun again. Perhaps one last way I can think of to visualize this, think of this as a race. So here's a racetrack. We're going to make the racetrack perfectly circular. And here's our race car. And here's Mars racing out here. Mars is a little slower, so what are we going to see? As we go around, we're going to see Mars come, and we're going to pass Mars. We're going to see Mars go behind us backwards. And that's exactly what we're seeing as we watch Mars rise in the east, and each day it's a little higher because we're going around there. We're looking at the imaginary sun is here, and the sun is staying in the same place with us. So as we are racing past this car, what's it going to look like to us? It's going to look to us like that car is going backwards. So we're looking to the east, and we see Mars, the Mars car come up, pass us to where we see it straight up at midnight, and then it's going to fall behind to where we see it off in the west. However, I'll make this track a little bigger. Here's Venus going faster. So we see Venus come up from behind and catch up with us and then disappear the other way. We see that it never goes to this side of us. It always stays here. So our view is to this direction. Then we're looking at that direction, that direction, that direction, that direction. And so think of it that way. I think it's maybe the best way to look at that. We're a race car going around. As we see Venus, we see it pass us. So it's going between us and the sun. We see it come up in the morning sky. Get further ahead, we see it go, sun is here, so we don't see it there. See it go behind the sun, comes back around in the evening sky, then goes back into the morning sky, behind the sun, back into the evening sky. Where Mars starts in the morning sky, gets higher and higher and higher as we pass it, and then disappears into the evening sky. Hopefully that clarifies why we see the planets the way we do. I don't know of any better way to illustrate it unless I had some animations, which I have no tools to make. So just imagine it. We're a race car going around the middle. The inferior planets, or Mercury and Venus, are going to go in this circle here, so we never see them far from the sun. So they go into the morning sky, behind the sun, back into the evening sky, between us and the sun, back into the morning sky, behind the sun, back into the evening sky, between us and the sun. Mars, on the other hand, I'll just go ahead and draw Mars all the way around. Mars starts, let's say it's over here. Now Mars is going slower, so we're catching up to Mars. As we catch it up, what do we see? Mars appears to go backwards. So we're stationary here. Mars first is on the other side of the sun, so it's in the solar glare, but it comes up into the morning sky. And as we get closer and closer, Mars appears to be falling further and further behind. Now, Mars is opposite to the sun, so it's straight up at midnight. And then it keeps falling behind. It's now in the evening sky. Keeps falling behind and eventually goes into the solar glare and we can't see it again. And so we see Mars going slower and it goes around that way, where Venus is going faster and goes around the way I described it. So the best way to understand that is to kind of imagine in this racetrack here to see why the planets appear the way they do. So I hope I made some sense out of that. You have to do some of the mental exercise on your own to understand why the planets do what they do. So if you found this useful and informative, please give me a thumbs up down below. It really helps the channel. Don't forget to subscribe and hit that gray bell when you do so you get notified when I put up new videos. If you want to learn more about astronomy, you can take my free astronomy class at vocatomy.net. It's 100% free. And to put these videos online and keep Vocatomy free, I depend on my patrons at Patreon. So if you want to help me make these videos and help keep Vocatomy free, you can go to patreon.com/Vocatomy and pledge your support. And of course, to make one-time donations, you can go to paypal.me/voced, V-O-C-E-D. So a big thank you to my patrons, and my one-time donors could not make these videos and do these classes without you. And thanks to everyone else for watching.